Okay, thanks for your patience on the change there. Our next speaker is Kelly Zhang, who's going to be talking about informed exploration.
Hi, thanks so much for having me. I just started as an assistant professor at Imperial, and today I'm going to talk about kind of building on some of the stuff that was mentioned in the Q&A of Claire's talk about using sequence models for exploration and trying to be principled about it. Okay, let me try to fix the. Oh, perfect. Okay. So a lot of my work has been focused on these decision-making settings in which there is an interaction between some human and some AI system. I've in particular worked in areas like mobile health, where you have some mobile health intervention, making decisions about engagement messages to people to help them move towards healthy behaviors, as well as like recommendation systems. And in these types of problems, there's a need to be able to develop decision-making algorithms that are able to incorporate like rich information, like image information, audio or text information. And additionally, there's a need to be able to have algorithms that are able to make decisions effectively in the face of uncertainty. So for example, in these systems, new users are constantly being added to the system that you have no historical information about. In recommendation systems, new content is being released that you have no historical information about. You need to have algorithms that are able to reason about uncertainty effectively and make decisions. Because in some sense, there's like constant newness in these decision-making problems. So kind of building on this, like a kind of shift that's happened in interactive decision-making is that there used to be like a bigger emphasis on algorithms that are able to learn from scratch. And instead now there's more emphasis on like, are we able to leverage foundation models for decision-making, for more sample efficient decision-making, and basically to provide a prior for your new task. Like, I don't need to start from scratch anymore. So in these types of decision-making problems, being able to make decisions effectively in the face of uncertainty, we need methods that are able to quantify our uncertainty and effectively manage this exploration and exploitation trade-off. And in this work, I'm going to focus a lot on bandit problems, which are very, very simple RL algorithms, which I'm sure most of you already know about. And these algorithms are designed to explore just enough, in the sense that they are designed to try to take actions to gradually get information about which actions may be optimal and learn to exploit those, and gradually learn to stop sampling the arms that are not good. And so, for example, in this little figure here, this red action, which you have a lot of uncertainty about, could potentially be optimal, but like this green action 2 is like unlikely. So the exploration algorithms need to take that into account. Thompson sampling is a very popular Bayesian decision-making algorithm that at a high level forms a Bayesian model of the environment, uses that any past data it's seen to form its posterior distribution belief over what that true environment might be. At each decision time, it's going to sample what like a plausible model of the environment might be and optimize decisions under that plausible sampled environment. And after taking that decision, it will observe some future outcome and then use that newly collected data to update its posterior. Okay, so just some background. And the challenge is now if I want a decision-making algorithm that incorporates a foundation model as a prior in some way, being able to reason about uncertainty is really hard. Like if my model of the environment, is a neural network with like 1 billion parameters, how do I effectively sample from this posterior distribution? This is extremely difficult, and it's like, are we able to quantify our uncertainty with these models where, like classic Bayesian models, you might form like an informative prior, but we barely understand what the models are doing. How can I form an informative prior? How can I quantify uncertainty? So the key idea in this work is that we end up viewing missing outcomes or missing future outcomes that you could observe as the source of uncertainty, rather than latent parameters that characterize the environment. So traditional like Bayesian modeling forms assumes that there's some latent parameter that is characterizing the environment, and we maintain a posterior belief over what that latent parameter might be. And Thompson sampling samples what that latent parameter might be and uses that for decision making. Instead, in this work, what we're going to do is consider like the future outcomes of future decisions I can make, or counterfactual past decisions that I didn't make. The outcomes associated with those decisions as the source of our uncertainty. And we're going to use like sequence models to probabilistically impute what those missing outcomes might be. And it turns out that we're able to implement Thompson sampling using these types of probabilistic generative sequence models. And as just a note, that it turns out that this approach is very deeply connected to this missing data view of causal inference and these ideas in multiple imputation that are very classical in the statistics literature. I have like one kind of slide here that if you know about Bayesian modeling, that typically in Bayesian modeling, one needs to specify a prior distribution and a likelihood distribution. These actually uniquely define a posterior predictive distribution. And it turns out that all of the work that I'm going to talk about is like, you can actually do a lot of Bayesian modeling if you only have access to this posterior predictive distribution, which is an autoregressive sequence model. Because it tells you the distribution of the next outcome conditional on the outcomes I've seen. Okay, and so now I'm going to talk about a simple motivating problem that is designed to illustrate the ideas in this work. So we consider a news recommendation task where we are trying to recommend the best articles to users who come to our website that is on average good for some large segment of users who arrive to our site. And in this problem, it's a meta-learning problem in the sense that each day I get a new recommendation task. Like there's a new set of articles that have been released. I have no historical data about what people like about these particular new articles. And I need to be able to reason about uncertainty and make decisions, recommendation decisions throughout this day. And the thing that is new or in our setting is that, or makes this problem a bit more modern, is that we want to use a foundation model to read these news articles to give us some indication of whether this might be a good article or appeal to this group of users that were coming to our website. At each decision time, a user arrives, the algorithm recommends an article, we see some vector of potential outcomes like whether they clicked on the article, liked it, or shared it, and the reward is just some function of these observations that we see following the decision. Okay, so I'm going to talk about our algorithm next. And I want to emphasize that in our problem setup, that there's actually two types of learning, and our algorithm is going to specifically tackle these two different types of learning. So the first is this meta learning aspect of being able to use data from like past days to be able to learn. We're going to use data on past recommendations from past released news articles to pre-train a sequence model. That's like a kind of meta learning component. This is offline, it's not online. Once we have the sequence model, we're going to use that for decision making in an online decision making problem given a new task. And we have some assumptions about like implicitly that each day is like a new task and that there's no like systematic trends within in how the day news evolves over days. We're just saying that like each day articles are being drawn from some distribution of articles. This is our simplifying assumption. Okay. So in step one, where we're meta learning using historical data, we are going to use our historical data to have a sequence model learn to impute outcomes. So we'll pick an article at random from our history. Here, Z represents the news article text. And so our sequence model is going to both ingest the news article text and any previously observed outcomes and predict some masked out outcomes. And it turns out that in order to attain, for a sequence model to attain low prediction loss, the model has to implicitly learn about how to reason about uncertainty given the text information. I think my next slide talks about this. So if my model is able to predict well, having observed just the news article and very, very few recommendation outcomes, then the model in that setting, if this model is effectively taking advantage of the text information, it should effectively primarily be using the text information because as affecting its prior in how it's making the decision. However, once the sequence model has observed many, many outcomes, effectively, the prior information should not be that taken into account anymore. And the model should primarily rely on these outcomes that it's seen. Like we initially thought this article would be very popular, but then after recommending it a bunch, we might realize, oh, it's not as popular as we thought. And we just rely on the actual recommendation outcomes that we've seen. And it turns out that this is very related to in-context learning and in-context learning models, and that this pre-training procedure is related to like empirical Bayes or methods to learn Bayesian models from data. Okay, now I'm going to go to the second part. So assume we have pre-trained our sequence model, and now we want to use it for decision making. So in my decision-making problem, suppose I'm on user 4. So in the past, I recommended article 2 to the first user, article 1 to the second, and article 2 to the third user. And now I need to make a decision for the next user. So what I'm going to do is I'm going to, for a particular news article, I'm going to feed in both the text and any past recommendation outcomes. And I'm going to probabilistically sample what this y hat outcome. I'm going to condition on that outcome. Oops, sorry. Not sure what happened. Okay, I'm going to condition on that outcome and probabilistically sample the next outcome in an autoregressive fashion and continue to do this until I've filled out this entire table. Once I filled out this table of outcomes, like this is a probabilistic sample, I'm going to basically fit my optimal policy, which here I would just take the mean of the outcomes in each of the rows and select the item with the highest imputed mean reward. Okay, and I want to talk a little bit about why does this generation need to be autoregressive? It turns out that this is very important. So suppose I have a news article and I've only seen basically one outcome. It's like I showed it to user 2 and they didn't click on it. How engaging is this article to the population? So let's say I autoregressively generate through this process the outcomes one time and get, okay, well, actually, it seems like in this sample that the mean reward is 0.7. Actually, this is a pretty engaging article. I autoregressively generate again, and I get that, okay, actually, the mean reward suggests that it's now not a very engaging article. And again, the article may be somewhat engaging. And the idea is that the variability across these generations is capturing the model's uncertainty in what the true mean reward is. You could imagine other settings where the news article is just so bad that across every time I autoregressively generate, I basically get a very, very like low variability, low mean reward. Okay, so I'm just going to talk a little bit about the theory because I thought it was very nice to be able to have some theory when working with these like potentially very large sequence models. The first result is that this is an implementation of Thompson sampling, especially when the sequence model that you've pre-trained is like pre-trained perfectly, then we show that it's exactly Thompson sampling because it selects actions according to the posterior probability that that action is optimal. The second result is related to characterizing the quality of the decision making. Even in the setting when your sequence model may be trained imperfectly. So basically, at a high level, we get a regret bound, which is comparing the quality of our decision-making algorithm compared to the optimal Oracle decision-making algorithm. And we are able to show that this is bounded by these two terms. And the first term is the typical regret bound that you would get for Thompson sampling if you had the perfectly specified Bayesian model. The second term is a penalty term that's related to the quality of the sequence model that you pre-trained. Basically, it has to do with the sequence prediction loss of that pre-trained model. And so the suboptimality of that pre-trained model ends up penalizing the regret. So this is pretty nice. I'm going to talk a bit about our empirical results. I'm focusing just on our like semi-synthetic setting. We also have synthetic settings where we explore like more simple settings, but in this setting for news recommendation, it's based on this MSN News article data set where they have like news articles and then recommendation outcomes. And we use that to build like a bandit decision-making problem. And we show that our this approach where we have a sequence model where the sequence model incorporates an LLM that reads in the text article performs the best. And we're able to, in the pre-training phase, end-to-end fine-tune the language model and the sequence model that's used to impute outcomes. And another thing that's nice about the theory that we presented was that we're not saying anything about the architecture of the sequence model that you use. It's just whichever one has the best loss. So we tried out many different types of sequence model architectures. Okay, and we also look at the quality of the uncertainty quantification. So what we can do is just as like I had in that previous slide where you may auto-aggressively generate out multiple times and look at the variability across those imputations, we can do that and form like a histogram of what we think the mean reward is and look at like, okay, a 90% credible interval, how often is the true mean reward in our interval? And it turns out that this approach is incredibly, has very good coverage and it's very well calibrated. It's on this like diagonal line in green here. And also that the widths of the intervals, uncertainty intervals that you get are relatively narrow. We also compared to some other like ensembling type approaches for uncertainty quantification. And we found that at least in our setting that they didn't perform very well. They were not very calibrated and they were just very like too certain and didn't quantify uncertainty, didn't capture the uncertainty well enough. Okay, the last thing I want to say is that we also have a contextual version of our algorithm, and it's like conceptually very similar as to what I've described, except now in the pre-training phase, you also incorporate contexts that are used to also predict what the future outcome might be. And then at the decision-making phase, after you impute this entire table of outcomes, you can fit the optimal policy with any policy class that you're interested in. So instead of just taking the means across each of the rows, we may fit like some other function to optimize your policy. And it turns out the choice of policy class you use affects the regret in like different ways. That's my talk, and happy to take any questions. And I will also be at a poster, I think poster